The recent DESI results, which are quite preliminary, suggest that dark energy, the substance that makes up the majority of mass in our universe, might not be constant. No one is retiring the cosmological constant, the theorized constant to which our best models attribute dark energy. But we still have no idea what dark energy is. There may be a clue, however, in a field of study that was originally developed to understand how to make more efficient steam engines. Thermodynamics has since become a set of laws that apply to everything in our universe. Back in 1995, in a rather astonishing result, Ted Jacobson derived Einstein's equations of general relativity, which explain the warping of space and time that give us gravity, from basic rules of thermodynamics. There had already been hints of this before from studies of black hole thermodynamics. Black holes were shown to have a temperature, and like all bodies with a temperature, they release radiation. In his best-selling book, A Brief History of Time, Stephen Hawking explained that this radiation was caused by particle-antiparticle pairs appearing in the vacuum of space. Normally, these come back together and annihilate one another, but near an event horizon, one might fall in and the other escapes, so they can't annihilate anymore. There was a nice illustration of it in the book showing the little particles. Some escape and some don't. This explanation is complete and utter nonsense, of course. Nothing like this occurs near black hole event horizons, and Hawking's academic papers on the subject had nothing to do with pair particles falling into black holes. This was just Hawking trying to explain something to the general public, and, being unable to do it correctly, made up an interesting lie. This radiation, called Hawking radiation, is caused by how an observer stationary with respect to the black hole sees the quantum vacuum near it. As this observer looks at the horizon of the black hole, the quantum entanglement between the vacuum outside and inside the black hole, from their perspective, creates a temperature. This temperature results in a release of energy, and it isn't only gravitating bodies that produce Hawking radiation. One of the founding principles of general relativity is the equivalence principle. This principle says roughly that there is no way to determine the difference between being in accelerated motion and being in a gravitational field. Einstein used the analogy of a windowless elevator that is being accelerated upward continuously. Occupants of the elevator would have no way of knowing if they are in a stationary elevator in a gravitational field or accelerating uniformly. That means that when we are in an accelerating reference frame, we should also see Hawking radiation. Although, like Hawking radiation, it has never been observed, this is called the Unruh effect. This is a beautiful result because it says that thermodynamics plays an important role not only in black holes, planets, and stars, but simply in an accelerating reference frame. This is exactly how Jacobson produced Einstein's general relativity from thermodynamics. Jacobson defined heat in spacetime as energy that flows across a causal horizon. This energy can be detected because it generates gravity, but from outside the horizon, you cannot know what is causing it. Horizons need not be black hole event horizons. They can simply be the boundary of our past light cone, all that which can causally affect us. Another kind of horizon that is more interesting is called a Rindler horizon, which is similar to an event horizon, but it is defined in special relativity as a horizon for an object that is constantly accelerating. Imagine a spaceship that takes off from Earth and constantly accelerates away. Because it accelerates constantly, a signal sent from Earth cannot reach it after a certain amount of time. The light beam will constantly try to catch up to it but never reach it. Now, if the ship were to stop accelerating, the light beam would catch up. It takes a constant force to keep the ship away from the Rindler horizon. Unlike a black hole event horizon, a Rindler horizon can be changed if the ship changes its motion. Also, it has no singularity. All the other features of event horizons, however, apply. Instead of Hawking radiation, the ship will see the Unruh effect. If it tries to send a signal towards the horizon, it will become redshifted until it effectively vanishes. If an astronaut is lowered to the horizon by deceleration, they will appear slower and slower until they disappear across the horizon. They won't be spaghettified, just marooned in deep space. If the ship maintains its acceleration, as with crossing a black hole, the astronaut can never return to it. Causal horizons like these are naturally associated with heat and entropy in particular because they hide information. If something from outside our past light cone, for example, affects something inside it, the information is hidden from us. All we can detect are quantum vacuum fluctuations resulting from entanglements across the horizon. These, of course, carry no information across the horizon. Yet there is a gravitational effect from that entanglement. Heat flows across the boundary. Dark energy has likewise been conjectured to be a form of thermal energy coming from a causal horizon, the cosmic future event horizon. This horizon is the limit that any future observer can observe in our universe. If the universe were static, after an infinite amount of time, this horizon would vanish and an observer, theoretically at the end of time, would be able to see all things that ever happened in the universe. Our universe is not static, however. As it expands, parts of the universe are no longer in the past light cone of our future observer. This creates a horizon. As Jacobson argued, any causal horizon hides information, and quantum entanglement across the horizon results in thermal energy. In other words, dark energy is the equivalent of the Unruh effect, or Hawking radiation, but comes from this future horizon boundary. Unlike a Rindler horizon, this future horizon is not an effect of our motion. It is an effect of the motion of space itself, and as quantum vacuum entanglements occur across that boundary, they appear as dark energy. While in ordinary horizonless space, these fluctuations have no gravitational effect. The existence of a horizon acts like a heat pump, pumping energy across. The reason why some physicists think that the cosmic future horizon is the culprit is partly because the math works out quite well. At first, physicists thought to use the Hubble scale rather than the future cosmological horizon scale. This is simply the inverse of Hubble's constant, and is roughly related to the size of the current observable universe, since it is the amount of time since the start of expansion till now. This gives us the wrong value for dark energy density, however, and doesn't even agree with an accelerating universe while the size of the future horizon does. Using the future horizon doesn't work perfectly, however, and some physicists have generalized the model. In particular, there is a question as to how we are calculating entropy. New entropy counting mechanisms, which change the amount of information exists in the microstructure of space-time, and therefore how big dark energy should be at a given epoch, give different results. There are Barrow, Salas, Renyi, and Sharma-Mittal entropies, all of which modify our basic understanding of how much information is contained in a horizon. Generalizing a model is often a good way to fit it better to data, but it can also make the model pretty useless if the generalizations have no observational motivation other than data fitting. Right now, we don't know if one of these models will turn out to be better than others. The Unruh effect, however, may be more far-reaching than future horizons and entropy formulas, because it says that for any point in space-time, there is a class of observers, accelerating ones, that perceive a horizon that has a temperature, and where there is a temperature, there is entropy. How can it be that a free-falling observer in space can perceive no temperature and no entropy while an accelerating one does? That comes down to the covariance of the quantum vacuum, and it means that thermodynamics itself depends on your state of motion. The same happens with a black hole. An observer that is hanging above the horizon will perceive it to have a temperature, while an observer falling freely across the horizon will perceive none at all. This means that the thermodynamics of the universe as a whole is dependent on the state of motion of galaxies and the cosmic microwave background. Given that, how do we account for the cosmological constant as a thermodynamic variable? There have been some small hints in the literature down this path. In a fascinating paper called Black Hole Chemistry, Kubiznak, Mann, and Teo argue that the cosmological constant is analogous to pressure. Unfortunately, the thermodynamics is far from simple in our universe because we are not in equilibrium. Rather, there is a tension between horizons inside our universe, such as event horizons around black holes and the cosmological horizon that surrounds the universe as a whole. These are at different temperatures, and as we know, when objects are at different temperatures, a non-equilibrium heat flow occurs. It is perhaps this tension and lack of equilibrium that makes solving the dark energy problem so complicated. Thank you so much for joining us today. See you soon in the next video, the next time.